All right, we're going to talk about RC series circuits. And as I've said, this is really just a review of RL circuits. Same thing, the only difference being the triangles are going to go down instead of up. Thank you. So, let's, guess I've got an arrow down. Okay, we're going to discuss the relationship of resistance and capacitance in RC series circuits. We're going to calculate all circuit values. And we're going to discuss power factors and angle theta in an RC series circuit. Again, as before, Z is the total impedance, which is, what is impedance? Total resistance to AC flow, and that includes the DC resistance and the inductive or capacitive or the combination of the two. Oh, that's for next chapter, sorry. Okay, so anyway, the total resistance to AC flow is impedance. We're going to find total current. E sub R is the voltage drop across the resistance. P is true power, and that's the result of the power going through the resistive part of the circuit. And capacitance, we know what that is. And E sub C, the voltage across the capacitor. Now, when we get into the problems here, we're going to find that the voltage across the resistor and the voltage across the capacitor are going to be greater than the total supplied voltage. How is that possible? Anybody? Because they don't happen at the same time, remember? What goes through the resistor happens at, let's say, time 0, right? And things that go through an inductor happen at time 0 plus 1. And theoretically, things that go through the capacitor happen at 0 minus 1. They happen before it happens in the capacitor, I mean the resistor. Now, how is that possible? The stuff that goes through the capacitor is so late to the party that it's early for the next party. Or so late for the movie, shall we say, that, okay, we'll see the next time it shows. So it's early for the next showing. See what I'm saying? It's called leading. But it really and truly, it's not really leading because it can't happen before the voltage occurred, right? It's just that the next phase of the capacitive current is happening behind when the original current happened. And so far back that it's in the next wave back. So it's leading the next wave, right? It's happening before the next wave starts off. So that's why it's called leading. Okay? And let's talk about a rule you guys should know. I fairly often forget about telling you about this anyway. But to remember that what happens in an inductor is lagging and what happens in a capacitor is leading. There's an electronics phrase that says Eli the Iceman. Write that down. Eli the Iceman. E-L-I-I-C-E. Eli the Iceman. And it means, I guess I'm going to start writing. Okay, what else are we going to talk about? Impedance. Okay, we don't need, I don't want to see Pythagorean theorem. Thank you very much. Why is it freaking out? Because I've got that in my hand. Stop that. There are no. There we go. Fighting with the thing. Okay, now here we have the typical triangle for capacitive things. Before we move on, though, I want to write this down. Now, the E stands for voltage, right? Everybody knows that, right? And what do you think I stands for? Current. Okay. And L stands for lags, right? No? What's it stand for? L for inductance. That's correct. This is a reminder that in inductance, L, remember R sub L? Not R sub L, X sub L? Inductance. This is the L out of the X sub L. Okay? And voltage is ahead of the current in an inductive circuit. ELI. In inductive circuits, voltage leads the current. And ICE, now there's no confusion about what C stands for. It stands for capacitive, right? And I and E are both in here, except now I is in front. So current leads the voltage in a capacitive circuit. So Eli, the I span, is just a way to remember that in inductive circuits, voltage leads the current. Okay, it happens before the current. And ICE is a reminder that in a capacitive circuit, purely capacitive circuit, that the current is going to lead the voltage. Now, there's no such thing as a purely inductive or a purely resistive circuit, right? So but we can say that mostly ELI in an inductive circuit, voltage leads the current, and in a capacitive circuit, the current leads the voltage. Okay? Those are opposite relationships, right? Because they are opposite functions. Okay, let's move down to our triangle. Let me see if I can get rid of the ink now. There we go. Now the slideshow will act normally. But I'm going to write on it some more because I want you to notice that the right triangle is off here to the right. Now, generally speaking, I don't draw this like this. I would draw this thing out here, right? Because normally we would have a triangle like this, right? We'd have our right triangle here. So when we flip it down, it should look like this one down here. So I'm not loving the way this triangle is, but it doesn't really matter. It's still a right triangle, and we can still deal with it, right? Okay, so R is still always the side adjacent. Every time, it's always the side adjacent. The side opposite. So as we look at this one kind of backwards to our normal thinking, right? We've got our right triangle here. We've got our phase angle over here. And we've got our hypotenuse coming across here as the longest side. So a side opposite is still kind of the same thing. And it's X sub C instead of X sub L. From our past studies, we were looking at X sub L, and it went up, right? The only difference was this triangle went up. Everybody agree with that? Mirror image. It would go up. Now, we still have R, as I said, and our X sub C. Now, is resistance of a circuit ever going to change? Can you change the resistance of a circuit? Not really. You're kind of stuck with that, right? If you've got a circuit and it's got a certain amount of inductance, you can change the inductance possibly by doing certain things, like maybe adding a capacitor. And it'll reduce the inductance. Oh, I'm getting ahead of myself. Sorry. So anyway, let's just look at this just like we did last week. If we don't know the impedance, let's assume we don't know the impedance. We don't know that. How would we find it if we've got these two functions? What are these two things? If we have this and this, what function is that? Oh hell, another hour of agony. Sine, cosine, and tangent. Which one of those do we have right now if we don't have impedance? We have the tangent, right? So if we wanted to find the angle, once again, this is the same thing as before. Let's find our tangent with our function. So second function, tangent. Now, it's O over A. So the O is the opposite, which is 16 divided by 12. Okay, so it's 16 divided by 12. Now enter. And it'll give you the angle, right? 53.13 degrees. Thank you. Okay. Now remember, this is our resistive triangle, right? Also, we're going to have a power triangle. Now, we're going to find, if we do some calculations, that we're going to get close to 20 ohms of total impedance. Let's find that, okay? How could I find my total impedance? I could use the cosine or the sine, right? Now, the angle itself is in my calculator right now, right? And if I want to say, let's say the cosine, because I want to find the hypotenuse, and I've got the side adjacent, right? I can punch in cosine, second function answer, in other words, use the last answer I found, which is the exact angle, and hit enter. And now it's going to give us the cosine of this angle. What is the cosine of this angle? Is it 8660? Oh, 0.6, I'm sorry. 0.60? 0.6 even, right? Okay, so what is that? What is that? What does that mean? That means that is the fraction that represents A over H, right? And we know the A, don't we? Okay, so let's just plug that in. The cosine, which is 0.60, is equal to A, which we know. What is A? This is the side adjacent, remember? So it's 12 divided by the hypotenuse, right? And we remember that we can exchange these, right? So we can rewrite this thing as H is equal to 12 divided by 0.6. So what is 12? Now, what's in your calculator right now? What was in your calculator right now? Wasn't it 0.6? Okay. We don't want to rewrite anything. We want to save time. So now we're going to put in 12, punch in 12, divided by second function answer, that last answer I found, and hit enter, and we're going to find that it's what? 20. I tell you, it's amazing. Pure functional magic. PFM strikes again. All right. Okay. Total current. Yes, we know the total current is the voltage divided by the impedance. We know that from, we would normally not write that. We would normally write P-I-E-Z, right? And that way we know that if we're going down, we're going to divide. If we're going up, we multiply. And if we have voltage times the current, the total current, what do we find? Somebody say apparent power. It's not true power, is it? Because the impedance represents a capacitive or an inductive factor, which means that our apparent power is what power is coming in, and how much of that we turn into power is related to our power factor, right? Okay. Let's see, voltage drop across the resistor. Voltage across the capacitor. We can find that with a triangle, right? Because we're not going to find it this way. And we know, we've already discussed this, that capacitance, in our last chapter we talked about capacitance, is 1 over 2 pi f x sub c, right? So C, the capacitance. What is capacitance? What's it measured in? Farads. Farads. The most common number is going to be in microfarads, but that's not the unit it comes in. Okay. Now, it's saying the capacitance is equal to 1 over 2 pi f x sub c. That's not the formula we had before, is it? We had x sub c is equal to 1 over 2 pi f c, didn't we? Yeah. So we can exchange them, just like our 1a over b is equal to c, and we can exchange our b and our c. Yes? Are you telling me that we can just exchange x sub c and that c? Whoops, sorry. Is that what you're trying to tell me? Whoops. Too far? Okay. There we go. Yeah, I think that's true, don't you? Okay. Well, another example of that, multiply both sides by c, divide both sides by x sub c, we'll wind up with x sub c is equal to, anyway. Okay, so x sub c is measured in ohms. Ohms, x sub c is capacitive reactance. And we find it, we can find our capacitive resistive triangle. Look at that. Now this is a voltage triangle. We did voltage triangles before, except we did them with inductance, right? So this is the exact same idea, right? So anytime we have two things, we find the function it matches, right? We write our O held another R of agony for sine, cosine, tangent, right? And we write our PEIZ. We start filling in things we know and finding things we don't know, right? Okay, so we could find any of these values that we don't have, right? And we would use a trig function. Oh, there's that nasty word, sorry. Triangle function to find it. Okay, true power. If we write our triangle again, I think it's going to give us a triangle. So let's go down to the true power triangle. Reactive power. Okay, the difference between the true power and the reactive power is where we're going to put them on our triangle. We're going to have apparent power is going to be our hypotenuse, and we're going to have side adjacent, which is where the resistance would go if it were a triangle in resistance, would be at the bottom, the side adjacent. And the side opposite, where the x sub L or the x sub C would go, is where our VARs go, our reactive power. So we know we have a triangle relationship all the time. Reactive power, apparent power, power factor. Power factor is the same relationship as the resistance compared to the impedance. And that in our power triangle is going to be the true power over the apparent power. It's still a fractional relationship, and when we divide the two, we're going to get the same exact number. What is the difference? One's going to be scaled up or scaled down from the other, right? They're just different scales. They're the same angle. And what's that angle called? Phase angle, angle theta. The phase angle is the same between the resistance triangle, the voltage triangle, and the power triangle. Now, if we're talking about a parallel circuit, we don't have a voltage triangle anymore, do we? It's all flat. It's all the same, right? Parallel, voltage is all the same. Can't have a triangle. What kind of triangle, what factor will we have a triangle for in parallel that we don't have in series? That would be current. Okay, so we're not going to deal with that a whole lot right here in this chapter. We're going to work with series, and we're going to work with voltage triangles, okay? Now, I don't know what this formula says. Cosine power factor inverse function is equal to 0. Oh, times the power factor. That's a really bad way of saying things. The cosine of phase angle is the decimal equivalent of the percentage. How do you turn a decimal into a percentage? You multiply it times 100. So we found the cosine of our last triangle was 0.6, right? If we multiply 0.6 times 100, we get 60. So the power factor of that triangle was 60%. Okay, forget about this cosine times power factor is equal to 0. That's not a good thing to think about. Forget that's even there. Number of degrees that the voltage and current are out of phase. That is true. That is not a terribly important thing. The more I look at this slide, the less I like it. Try using the inverse or second function on your calculator to convert between the power factor and theta. Well, we do that already. Thank you very much. Okay, RC series circuits, that they're out of phase. We know that. But let's look at a problem. Oh, we like that. Except now we have two capacitors in series, right? Now, how do capacitors in series add up? The exact opposite of the way we treat a resistor. And so a resistor in series, we would just add up, but a resistor in parallel, we add the reciprocal. So if we're going to add capacitance, we're going to add the reciprocals together, right? To get the reciprocal of the total. Everybody agree on that? Everybody understand what I'm saying? That's not just for the resistance. Okay. Circuit with values. I bet we have a triangle on the next slide. I hope. It's not going to talk to me. Okay, so we're going to talk about what we've talked about. The amount of phase angle difference between the voltage of the current in an RC series circuit is the ratio of resistance to capacitance. Shocking. True power is produced by the resistive parts only. Power factor is the ratio of true power to apparent power or the resistance to the capacitance, right? In a series circuit, the current is the same through all components. Okay? So therefore, we don't have a current triangle, right? Because it's flat. That triangle is flat, 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 right? All three sides. Not much of a triangle. And that's it. Now we just want one more slide. Let me stop while I get a clear slide. Okay, so we picked a problem, and we decided that we didn't pick a resistance. Let's find our X sub C first, and then we'll pick a resistance. But first, let's find our X sub C. Hang on one second. If we've got 20 microfarads, oh, I'm sorry, you're right, it does. Okay, back to microfarads. We have the formula for X sub C, which is in ohms, is 1 over 2 pi f times C. And we're going to say that we have 20 microfarads. So our shortcut for 370 is 377, assuming we have 60 cycles per second. We're going to assume that for the moment. So we have 1 over 377 times 0.000020, right? That's 20 microfarads. Everybody agree with that? Okay. Now, we're going to wind up with a number over here. Now, what we're going to do is we're going to do the handy-dandy TI-30X2S method of this and make it simple for ourselves. Okay, so hit clear twice, because this is a new technique we're going to use, and we're going to use this a lot. Okay? So we're going to isolate this bottom part all by itself first. Is that okay with everybody? Okay. So let's hit clear. We already did that. Now hit 377 times 0.00002 is equal to. And that's going to give us a fairly small number, right? Okay, now that is 1 over C, 1 over 2 pi fc, right? That's the reciprocal of the answer we want. Now hit x to the minus 1. Now hit enter. How many? $132.63 ohms. Okay, now you can see why I wanted to wait to pick my resistance, because we don't want to have some crazy number like 12 ohms and 132 ohms of X sub C, because things are not going to line up very well, right? So let's just pick a number of, let's say, 150 ohms. Would that be okay with everybody? Okay. Because what we're really looking for is what is our Z, our impedance. So now what sides do we have? Here, let me put this in over where it belongs, and maybe it'll be visually appetizing that way. 132.63 ohms of X sub C. So now, as we look at the angle, we can see this is the side opposite, right? And this is the side adjacent. Everybody see that? Okay, so we have the side opposite and the side adjacent. Which of these functions do you like for that? The tangent. So we can find our angle now, right? Now hit clear. I know I don't say that very often, but we're going to hit clear now. Matter of fact, hit it twice, just to be sure. So now we're going to say second function tangent. And in the tangent, the opposite goes first. So we're going to put in 132.63 divided by 150 is in, and hit enter, and that'll tell us the angle of this thing. Say again. (41.48 degrees) is our phase angle. Okay, and we're going to have our impedance. We're going to get that from that. So now our angle is in there, 41.48, and a whole bunch of other numbers, right? But we want something else. We want the cosine for the moment. Let's get the cosine. So we would put in cosine, second function answer, enter, and that will tell us the cosine of 41.48 degrees. And what is the cosine? No. There we go. 0.7500. Okay, now I want you to notice that since the cosine represents the power factor in decimal form, this thing's going to turn 75% of its apparent power into true power. Everybody see that? Because it's the cosine is the power factor. The power factor is what percentage of the incoming apparent power is going to be turned into true power. So we can now see that once we get to true power, we can find the true power very quickly. Okay, so let's get rid of a little bit of this junk. Hang on one second here. Okay, and I think I want to get rid of that. I think so. Because I no longer care about the impedance, do I? Somebody remember that it's 132.63. That, or I just want to write it a lot smaller. How's that? How's that? Better? So we now know that our cosine is 0.75, right? Now let's write down what we know. We know that the cosine is 0.7500, and that's equal to A over H, right? And we're looking for the hypotenuse, which is H. So we're going to plug in our A, aren't we? What is our A? Our side adjacent is 150 ohms. Everybody agree with that? Anybody disagree with that? Good. So now we have that thing again where we're going to exchange the number on the left with the thing on the bottom over here on the right. Okay, everybody see that? So we're going to have H is equal to 150 divided by 0.75. I have a question. What number is in your calculator right now? Is it 0.75? Okay. So all we need to do is put in 150 divided by second function answer, the last thing we found, hit enter, and it's going to tell us the hypotenuse. 200.22. That is our total impedance. Okay? So now we can find some other things out, right? Leave that in your calculator, and we're going to put in 120, punch in 120, divided by second function answer, enter, and we're going to find our current, aren't we? Because we're going to get 120 divided by 200.22. 0. Oh, it's 0.5. 0.5993. I like 0.6. That's not so bad, but I wouldn't round just yet. Because now, what do you have in your calculator right now? 0.5993, right? You've got that long, accurate number. Now hit times 120, enter. Still hadn't hit erase for a while, have you? So what number are we going to get? $71.918 VAs. That's how much apparent power we're making. We're pulling in that amount of power. Because if we've got 120 volts, and we're flowing 0.5993 amps, we're pulling in 71.918. Now, before I even go to the next triangle, you know what's going to happen, right? We're going to take some of this stuff out. Now, we're going to get this out of here. Let's leave that. We want to get rid of all this. Let's see. We don't care about this anymore. We don't care about that. It's not R anymore. Let me fix my triangle here. It's all screwed up. I don't know how that happened. And now we said that the bottom line on our previous triangles was always resistance or true power, right? Well, the resistance is still where the resistance is. It's that bottom line, the side adjacent. So it's not resistance, it's true power. Okay, our apparent power is going to be the hypotenuse, right? And that is 71.918 VAs. Everybody agree with that? Okay, let me get rid of... Oh, is the angle still 41.48 degrees? Same phase angle, right? Okay, so we now have our apparent power. We've got one side, and we've got the angle. Everybody agree with that? Okay. We even know the cosine ahead of time. If we take the cosine of 41.48, what do we get? 0.75, right? Everybody agree with that? So the cosine of this angle is the power factor. Now let's plug in some numbers. Let's do it the hard way. The cosine of theta is equal to A over H. Everybody agree with that? Okay, let's plug numbers in for what we know. We know the cosine is 0.7500, 0.7500. Now the A, we don't know. But we know the hypotenuse is 71.918 VAs. Everybody agree with that? So if we want to get A all by itself, the side adjacent, the true power, we can multiply both sides by 71.918. And we'll get 71.98 times 0.75. And this will drop out of that side. Times 0.75. So what's in your calculator right now? 71.918? Excellent. Times 0.75. $63. 53, sorry. 53 what? Watts of true cranking force or real work getting done. 53.9388 watts of work is getting done in the circuit. Okay? Everybody clear on this? Anybody foggy, confused, questions? Any questions at all? Yes, sir. 938. That's the true power of the circuit. That's the true power of the circuit, the work that's getting done. 71 is the apparent power. That's what you're paying Edison for, 71.918 volt amps, VAs. But on your bill for medicine, it's going to say watts, but it's a lie. Because they're going to supply you with VAs, and you're going to do whatever you do with it and make efficient use of it or not. All right, that wraps it up.